Good morning. I must apologize for Michel. I got a message Tuesday night that he couldn't make it. He had another emergency call. The Future Circular Collider study, I will be giving the report on the project. That is the design study, which is taking place. We started lobbying for this back in 2010, 2011, and finally got the design study going in 2014 after several important papers. The team is very large now. You can see this is a photograph taken from the top of the mountain, which is behind CERN. And of course, when you look, it's very rare you see anything like this. Okay, most of the time it's full of clouds. But even more rare to see the accelerators underground. And the PS, SPS, the LHC, possibly a high-energy LHC, and the FCC, which in order to make 100 kilometers has to go behind that mountain, which we think from CERN is the end of the world. But actually, there's another plane behind that, so the ring can actually be sitting on reasonably flat ground over the 100 kilometers. So that study was launched with the clear view that this should be the study of all the machines that can fit in a 100-kilometer machine. Very importantly, the proton collider was set up as long-term goal in order to make sure that that ring could host a 100 TeV collider. Now, 100 TeV is what corresponds to 16 Tesla magnets. If somebody makes stronger magnets, you can go higher. Or if one needs to lower the field just to be sure that it works, you still get a huge factor of increase of energy compared to the LHC. So it's a very non-risky number. The constraint is to stay around Geneva because it has to be connected to CERN somehow and run by CERN. And that you see what is the possible ring. I mean, this mountain is actually not completely avoided, as you will be seeing. The E plus E minus collider is seen as a potential first step. It's not necessary it happens, but in effect, it is the thing which is foreseen to take place first. An alternative way to go to the 100 TeV machine would be to implement these strong magnets in the LHC tunnel as the first step. And that's part of the study. We also have the option of having an electron-proton or hadron-proton collider and also having heavy ion colliders in the PP machine. Now, this is contemporary to the FCC HH. You need the hadron ring to do this, while the electron machine comes first. So the physics has been summarized in three little paragraphs here by Michel. The main point is to explore the 10 to 100 TeV energy scale by very precise measurements. Of course, these particles have to have standard model couplings in order to be seen. The improved precision on many electroweak quantities is given by the increase in statistics. Now, that would be nominally a factor of 250. Most of the time, we stay shy of that because in order to convince yourself you can improve by a factor of 250, you need to do a lot of work, which we didn't have time to do, and you need to understand the problem in detail. But certainly, factors between 20 and 50 are possible on all these quantities, and there's a very long table of this. That includes all the electroweak measurements, including tau physics, the Higgs, and top quark coupling. These numbers will be very important for the full exploitation of the Hadron Collider. So the machine designs looks for the highest possible luminosities across the available energies. The FCCHH aims at 100 TeV, and then you get typically sensitivity for particle production at, in the 20 to 30 TeV range for excited quarks or such very visible objects. Huge production rates for single and multiple production of standard model bosons, so Higgs's in 10 to the numbers of 10 to the 10 or so, W's 10 to the 13 W's, and Z's, and also top quarks. So the machine design aims at 20 inverse attobars in 25 years. HELHC is simply replacing the LHC magnets with 16 Tesla magnet technology. It's actually much more difficult than this. And the aim is to get 4 times the luminosity of HLHC. And this means this has to be in the LHC tunnel, no re-digging of it or anything. So the FCCE is a double ring machine in order to have the 20,000 or so bunches in the machine that you need for the Z peak. The machine is designed in such a way that you need a top-up injection, so the machine stays, the collider stays at the top energy all the time, and you keep injecting into it with a booster, which would be on the same line as the Hadron Collider. The collision points are shaped this way so that the incoming beam arrives in straight line, and the curvature is after the interaction point, so that the synchrotron radiation into the detectors is minimized. The design has been laid out with 2 IPs. If you really want, you could imagine to redo the design for 4 IPs. You need more than just 2 caverns. You need also to extend the ring for all this separation of the beams around the IPs. But it's certainly technically possible, and the luminosity, we haven't seen any difference between 1 or 2 interaction points. The injection booster takes care of making sure there's enough beam all the time. So probably the luminosity scales with the number of IPs. The crab waist optics is used in order to be able to reach high impact beam parameters at the lower energies. And the synchrotron radiation power was set to be a total of 100 megawatt. So that's 50 megawatts per beam at all beam energies. The synchrotron radiation is only 30% of the total budget of energy of the machine. And so it's in your interest for a given luminosity to have as much beam as you can, because all the rest is overhead. Top-up injection and booster in the ring. This is the table of parameters. I'll just point out a few. The beam current is amperes at the Z, and you can see that it decreases very fast with energy. The number of bunches also decreases very fast with energy. At the top energy, it's only 48 bunches. At the Z is 16,640 bunches, which makes a beam crossing rate of 25 nanoseconds. The bunch intensity is more or less stable. 36 MeV energy loss to 9 GeV energy loss. So you see the machine has very different regimes across the energy spectrum. And that is seen in the RF voltage. You only need 100 megavolts of acceleration in the Z machine, and you need the full 10.9 gigavolts at the high energy. This you need twice. You need once for the collider and once for the accelerator. The low energy, we use the separate cavities for the electron and positron beams because they have to take so much current. At the high energy, we take one single set of RF cavities for everything. I think everything else is more or less straightforward. The luminosity is 2 × 10⁻36 or more per IP, 2.5 × 10⁻35, 7 × 10⁻34, and 1.4 × 10⁻34 for each IP. This is a graph that Frank redid. This is the luminosity of FCC, CEPC. And you can see that there's those lines continue more or less straight below. So clearly, this is an ideal machine for the study of those 4 particles that we know, and which are the 4 heavy particles of the standard model. The interaction region, so these asymmetric points, that leads to interesting shape in the vertical dispersion, which you can see the vertical dispersion is 0. The horizontal dispersion varies significantly around the interaction point. And as well, the beta functions, as you can see here, have been designed. And the important thing for the chromaticity is the families of sextuplets, which you can find here. Now, the machine has been designed in such a way that you don't need to reinstall the machine for each change of energy. It's a 60-degree lattice for Z and W, as we had in LAP, and 90 degrees for ZH and TT. And those of you who remember LAP, these numbers kept changing, and we kept recabling a little bit the machine to improve such things as coupling and optics, etc. But this basically can be done by sticking to the same accelerator. So the operation model, we plan to start just like LAP, to start at the Z, and then you go to the Higgs, and then to go to the W, and then the Higgs. We studied a bit what kind of running mode optimizes the physics output. And we ended up with basically 3 years at the Z. In fact, it will be 4 years because we plan to have 1 year for commissioning in that lot. The W, this is tailored to measure the W mass to half an MeV. And then the Higgs is the big part of the first iteration of the machine. That point is where you measure the ZH process and determine the Higgs width, which is an essential parameter for the rest of the, for all the Higgs coupling measurements. Then we go up to the top. There's quite a bit of RF to install, so that will take a year of shutdown. And we get to 1 year to measure the top mass, and 4 years to improve the Higgs measurements and the top quark measurements. So basically, the total program fits in 14 years, including the machine modifications, in 2 phases. The RF installation defines the staging of the machine. And that's an important point when you talk about money, because you don't have to pay all the RF at the start of the machine. You basically have these 400 megahertz monocell cavities with only 100 megavolts per beam of acceleration. But those are important because they carry a lot of current. Then when you go to higher energies, W, Higgs, and top, you can use 400 megahertz four-cell cavities. And for the TT bar machine, the strong voltage is obtained by 800 megahertz 5-cell cavities. So this is the running plan of the machine, starting with 2 commissioning years, full intensity Z, W, Higgs, a year of stop, and then the TT bar operation. The RF cavities R&D is happening all over the planet. We have collaborations in Orsay, in JLab, in Italy in this case, and CERN has its own program within the EasyTrain European training network. Now, this is the 800 cavities. The quality, this is 35 megavolt per meter here. The limit is 31 megavolt per meter, and the operation range is 18 or 19 megavolt per meter. And you can see that this is well achievable. So this is an interesting technology where the electrohydroforming is used. You generate waves, thank you, in the water to mechanically form the cavities. The power consumption is an important aspect, and this has led to designing basically this double ring machine. Is a single string of magnets. This is the dipoles. You have the electrons in one side and the positrons on the other. And the quadrupoles as well. This is a single magnet with two apertures in it. This helps keeping the power budget at a low level. So this is little pictures of it. The vacuum system is similar to what is done for the Super Cake B. Sort of round vacuum with a horizontal winglet on the side to absorb the synchrotron radiation and avoid the electron feedback. Synchrotron radiation absorbers with neck pumps into it, and the construction of prototypes is happening within the coming months in integration with those magnets. So this has been prototyped. This is not really rocket science, those dipoles, but they're very important in the power consumption of the system. The injector, there are several schemes for injecting in this machine, that is injecting in the booster ring. You want to inject at about 20 GeV, like we did in lab. And that fits very well with the CERN SPS acceleration, as we had for lab. You start with a LINAC. You produce the positrons at 4.46 GeV of the LINAC, and you store them at 1.54 GeV in the damping ring. And then go into the SPS to 20 GeV and into the big machine. Now let me come to the proton-proton collider. This is the table of the LHC, the HL-LHC, HE-LHC, and FCC-H8. So the beam energy increases, the collision energy increases. The magnetic field here is at LHC is 8.33. HE-LHC would be 16 if you want to get to about 27 TeV in the center of mass. The circumference, of course, is much bigger here, which gives you much better certainty of a big increase in energy. Bunch intensities are here. The important parameter is the bunch spacing. At this point, no attempt was made to make a design that has faster bunch spacing, and therefore, at the luminosity that we're talking about, 3 × 10⁻35 per square centimeter per second, you end up with 1,000 events per bunch crossing. Now, I am sure somebody will want to try to fit 5 nanoseconds or 12.5 nanoseconds into this. Now, something is new with this machine that, unlike the LHC or even HL-LHC, we're starting to get significant synchrotron radiation from the protons. In FCC-H8 is 2.4 megawatt per beam, so 5 megawatt total. It's 5% of what the electrons do. If you think of one day having 40 Tesla magnets, that number will increase to the 4th power, okay? And it will become a real synchrotron radiation machine. So that makes a big difference in all the details of the design, vacuum chamber, etc. But it helps also for the operation of the machine. So HELHC, that's the first task. The first time people designed the FCC-HH magnets, tried to put them in LHC, it doesn't fit. Okay, too big. So it has to be reduced in such a way that you can actually bring in new magnets and fit them in position. And that has implications both for the QRL. This has to be new. People thought we could use the existing one. That doesn't work. You have to make a new one. You have to squeeze the magnets in such a way that it all fits. There have been many iterations for the 16 Tesla dipole magnets. It's already difficult to make a 16 Tesla magnet, but to make it such that it fits in the LHC tunnel is a further challenge, and the result is immediately that they are leaking magnetic field lines. Yes, thank you. So this work has been taking place in various labs and so on, but people managed to make designs which work. Other problem in the HELHC, well, clearly you need more cryogenics for that, and that means several new points of 1.8 degree refrigeration units. Optics, let me skip this for the sake of time. Layout and optics is here. You see two interaction points, two additional interaction points that could be the FCC-B and the maybe Alice FCC type of experiment in addition to the FCMS and FATLAS. There is a region for beta collimation and the extraction and dumping of the beam. That's a scheme of how the luminosity will evolve with time. In the first phase, it is expected that with beta star equal 1.1 meter, you get luminosities of 5×10⁻⁴, and slowly decreasing, you refill, etc. If you push the luminosity by lowering the beta star, the first thing that will happen is that the luminosity will actually increase because of the radiation damping. And then you're going to have shorter fields, but much higher luminosity. Injection systems from the LHC or from the SPS have been designed. The important key thing for this machine, of course, is the high field magnet R&D, and there are many institutes involved in the design and improvement of the wire to go from the present performance of the LHC to an increase of 50%. That's partially how you get to have smaller magnets. And so you can find some Costera magnets designed in INFN, in France, in Spain, in PSI in Switzerland with this counted Costera design, and in the US. Short magnets will be built in the period from 2018 to 2022, so there's about 4 years of prototyping to understand some of the problems better. Also, a Russian program was created recently. 15 Tesla dipole demonstrator in the US, so you can see all the laminations, the scheme. The thing is actually being built, and you see what things are starting to look like now. And the first magnet test will be made in September this year. So that's an important milestone to have these big magnets starting to be developed. This ERMC, this is a racetrack magnet coil, is being assembled at CERN to test the resistance to for instance, quenching and so on, the mechanical reaction. And that is happening in the test facility at CERN. Synchrotron radiation, I mentioned, is important. You need to have you need to have a way for the synchrotron radiation to escape. So this is how it is designed. You have an escape here, and it gets absorbed not in the primary shielding, temperature shielding, but behind, so that it is absorbed at a higher temperature than the 1.8 K. Otherwise, this would be terrible for cryogenics. This has been done tested in the beam in an electron machine in Germany, and you can get a similar synchrotron radiation from a 2.5 GeV storage ring, electron storage ring, as you have from the 50 TeV hadron collider. So finally, cryoplants. You need to keep things reasonable between the beam screen temperature and the refrigerator power. And basically, these curves show you that we want to be about in this place for the having a beam screen at 70 K. Okay, now the more strategic bit, the location of the tunnel in the area. As I mentioned, there's only one little piece of mountain we have to go through. Otherwise, it's a very nice terrain, the morass. 0, 3 exclamation marks. So that means that with the exception of this limestone, which is here, everything is more or less more straightforward than it had been for LEP, because we were trying to get under the Jura out there. So low risk, fast and cheap construction. Large caverns have to be located in point A and point G. I think that works okay. Then we have to see what the buildings will look like on surface, and that's where the population will start getting alarmed, I suppose. But the interactions with the population are generally extremely good. So this is what the machine will look like. This is the electron machine. It looks ridiculous, and then you get the hadron machine. Timescales, you need to do a study like was done for LAP, where you start excavating somewhere where you can bring in the magnets, and then you bring in magnets, and then somewhere else you excavate. And the total construction is 7 years, and the first sectors are ready after 4.5 years. So finally, this controversial plot, I think this is very important. Basically, the message that you have to take is that the next machine at CERN can happen as soon as HLLC is finished. Okay? There's no way you get anything else before because of the power consumption. So it has to be just like that. You finish HLLC, that's when you put you have the next machine. If you want to have HELHC, you're going to have 6 years of installation. If you want to have the FCC itself, you have to make sure all these production of magnets can work. The FCCE does not have any of these other problems. You just have to get enough money to dig out the tunnel, and a few years later you have the FCCE exactly when HLHC finishes. If HL finishes decides to finish earlier, that machine can be pushed forward. That's not an issue. The machine is buildable. Of course, you need money. None of these projects can fit within the CERN budget. So you have to squeeze and work to get a little more money, but they are not that far away. I mean, it's all similar to the LHC. And anyway, that's discussion for the roundtable. Anyway, this big collaboration, it's happening. CERN is taking this very seriously. It will be in the strategy. And thank you very much.
Thanks, Alain. Unfortunately, we are out of schedule, so we have time for one question. Okay.
There is a word in your this presentation which it's a tricky word. Considering the FCCEE as a potential first step, I think it's very risky option. I think the idea with the FCCEE and all this electron machine is to define which is the scale we have to look for, because the deviation from the standard model will give this indication. So the idea to go directly to the FCC-HH, I don't think it's a good idea. What is about your opinion?
Oh, my opinion is that the best we can do as a Higgs factory, as a search factory, as an exploration machine, is to FCCE and then FCC-HH. That is a fantastic physics program. It's also technically feasible. It matches what we know how to do. And we will, basically, once you get the electron machine in the tunnel, it's only a matter of time that you get the hadron machine in it. So that defines the CERN program for another 60 years or so. Now, new physics can come from places we don't expect. Okay, so with this caveat, but really here we're taking the broadest possible picture with the electron factory and with the hadron machine.
Yeah, I agree it can come, these new discoveries, and in the past it happened. But still, if it's better if we can have some hints. And by the way, why? I mean, going to 27 TV for this high energy LHC, it should be also be justified. Of course, we have the tunnel, we have everything, but I mean, it should be justified somehow. It's the same question as was asked in the beginning. I mean, we cannot go like this because we know that in the past we discovered many things by doing things, okay, but now it's much more expensive than Becquerel experiment.
Right, so we have to do clever planning, and that's exactly what this is trying to do. I think we are here impinging into the roundtable discussion of Saturday, and this has been the case for the previous speakers as well. But honestly, the thing which you see immediately is that HE-LHC is not just replacing the magnets. There's much more to it. There's also the injectors, which are not quite appropriate. So it is likely, I don't see, the cost of HE-LHC is larger than the cost of that new tunnel. Okay? So that gives you, the cost of the additional cost of the electron machine compared to that is small. So that gives you a picture of where we are.
Okay, let's thank the speaker again. Let's go to the last talk of this session.